last session of the conference. And the first talk today will be on Zoom by Professor Mark Haskins from Duke. And the topic is recent developments in G2 Laplacian flow. Do you hear us?
Thanks very much. Can everybody hear me okay?
Yes.
So first of all, I'd like to offer my apologies for not being there in person. It was certainly not my intention to be giving the talk by Zoom, but weather and airline problems meant that I couldn't join you this time. But I hope to be able to make it to Rio sometime in the not too distant future. So, yeah, what I would like to do in this talk is to give a little bit of a overview of some recent developments in Laplacian flow. It will obviously be a somewhat biased overview that will concentrate on developments that I've been involved with. So there are various collaborators in different parts of this. So some of them at least are with you. So Johannes Nordstrom from Bath, and then Ilyas Khan and Alec Payne from Duke. But then there's also another collaborator, Rowan Junman, who's a PhD student at Bath. So since I haven't been able to join you for the rest, I'm not quite sure exactly who has said what. So let me just start with a very quick overview slide, which hopefully everyone is really just to set the tone, etc. So if we think of G2 as, say, the automorphisms of the octonions, then we can get a G2 invariant 3 form on the imaginary octonions, just as we do out of the imaginary quaternions by using octonionic multiplication and the Euclidean inner product. So we take the cross product as the imaginary part of the octonionic product, and then we take, to get a 3 form, we take the dot product of a third vector with the cross product u and v with w. So then we can use this as the local model on a general oriented smooth 7 manifold. So we can look at 3 forms where there is some isomorphism between the tangent space and R7 that pulls back 3 form to this standard model that we just discussed for some orientation preserving isomorphism. And then a 3 form on a 7 manifold is positive if it's a section of this bundle. So at every point, it belongs to that space. And then every time I have a positive 3 form, then that defines a reduction of the frame bundle of your manifold to a principal subbundle with fiber G2. So in other words, we get a G2 structure on M that has that induces the given orientation. So we can think of positive 3 forms and then the same thing as oriented G2 structures on M. But typically, we're not just interested in all G2 structures. So we're most interested, for instance, in G2 holonomy structures. So we know that because G2 is a subgroup of SO7, then it has an induced metric. So we'll write that G sub phi. So if we have M phi G phi, a G2 structure, and then if it satisfies the system of PDEs that D phi and D star phi are both 0, where now phi, D star phi is defined using Hodge star with respect to G phi, then we know that the holonomy will be contained in G2. And then under some good circumstances, some topological restrictions, then we can actually force, in many cases, the holonomy to be the full G2. So we'll call such a G2 structure satisfying that system of PDEs a torsion-free G2 structure. So it really is, you can talk about the torsion of your G structure, and this really is the torsion of it vanishes. And of course, we notice that this is a nonlinear PDE system because G phi depends nonlinearly on phi, and then D star depends on the Hodge star, which depends on G phi. And then if we just look at these equations, then we see that these torsion-free PDEs form a first-order system. And so we've got the condition of being a positive 3 form is an open condition. So we have 35 coefficients. And then naively, we have a 4 form and a 5 form both vanish. So that naively looks like 35 plus 21 conditions. But there's some overlap of 7. So we end up just with 49 equations for 35 unknowns. But in any case, it's an overdetermined diffeomorphism invariant system, and so it's not the kind of PDE that your analyst friends are likely to love. And so, of course, after Robert Bryant's work, then we know that there were lots of local solutions thanks to the methods of overdetermined PDE, and then if we want to deal with solutions on compact manifolds, then so far there's really only been one approach that I'll call the elliptic approach. So at a high level, it's a singular perturbation method due to Dominic Joyce. And at this stage, all known constructions of G2 holonomy metrics on compact manifolds use this approach. So the approach with the idea of the approach is, well, we somehow construct a 7 manifold and a G2 structure on it, which we show to be closed. And then, so we've satisfied one of the 2 equations. And then rather than asking that D star phi is 0, we somehow arrange something so that D star phi is sufficiently small. Then the condition, so now we can consider perturbing this 3 form phi by so staying in the same cohomology class, so we can add d eta and then get some new 3 form phi tilde, and then we can ask, well, what's the condition that phi tilde satisfy these torsion-free PDEs? And then that turns out to give you a nonlinear elliptic PDE for this 2 form. And then because we're assuming that d star phi is sufficiently small, and I'm being vague here, then we can expect that you might be able to solve this by iteration, so by solving a sequence of linear problems. So that is indeed what one can do. And then the difficulty becomes reduced to, well, how do you actually find initial closed G2 structures that happen to have sufficiently small torsion? And all the constructions here exploit various potential degenerate limits. So the original constructions of Joyce were these generalized Kummer constructions. So you take a flat 7 torus quotient by an appropriate finite subgroup of G2 and then try to resolve singularities. Later constructions like the twisted connected sum construction involve something where a parameter is involved in which a long cylindrical neck appears, and then you could start by thinking of taking 2 asymptotically cylindrical objects and trying to put them together to get a compact one. And then more recently, there are ways to try to generate examples that exhibit some sort of dimensional collapse. But I don't want to say too much about that because that's not going to be the focus of the talk. But so far, if you really do want to find a compact G2 holonomy manifold, then the only way to do it is via this elliptic singular perturbation theory. However, you could at least consider trying to use instead a parabolic PDE approach, so a flow approach. And that's what I want to discuss for the rest of the lecture. But the warning at the moment is that we cannot yet construct anything by the parabolic approach that you wouldn't already have known about from the elliptic approach. So, but perhaps in the future that will be different. But this is a sort of long-term approach, and then if you personally want to try to find some more compact G2 holonomy manifolds, then you should probably stick to the elliptic method for the moment. So there's not only one possible flow of G2 structures, but there's only one that I want to talk about now, which again lives in the context of closed G2 structures. So we want to think about something that's going to evolve the underlying three form. So we say that something solves Bryant's Laplacian flow if the time derivative of this one parameter family of closed G2 structures evolves by just the Laplacian of that three form. And so if we start with something that is closed, then throughout this evolution, then the family of forms will stay closed. So this is it.
Hello? We don't hear you. Is there anybody? Hello? Mark?
Everything's frozen. It looks like
It's probably the connection. Maybe it's his connection.
seems his fault. It looks like the Wi-Fi there, maybe, possibly.
Can you hear me again? Something happened with my internet connection.
Yes, we can hear you.
Okay, apologies. So if phi t evolves by Laplacian flow, then gt, the induced metrics, they evolve by something that at highest order looks like Ricci flow, but with some important correction terms that are quadratic in the torsion of phi. But at least this is somewhat promising that that the flow on the level of the metric looks somewhat like Ricci flow. But so a few first observations. Well, so if I take a torsion-free G2 structure, then that's closed and co-closed, so the Laplacian of it is 0. So this is a static point, a stationary point of Laplacian flow. And indeed, those are exactly, the stationary points are exactly the torsion-free G2 structures. So that's something that we might hope for. Another good feature of the Laplacian flow on closed G2 structures is that unlike Ricci flow, then it does actually have a sort of obvious, nice gradient structure to it. So given a G2 structure, then we can talk about the Hitchin volume of phi. So we just take phi, wedge with star phi, normalize by some convenient constant, and integrate that over a compact manifold. That's the Hitchin volume. And so now we can start with some closed structure phi 0. We can just consider variations within the same cohomology class, and then Laplacian flow can be seen to be the upward gradient flow for this Hitchin volume function. And so similarly, then we can ask, well, what are the so first of all, what are the nature of the critical points of the Hitchin volume functional? So it's well known that those are all maxima. So this is sort of in keeping with this being an upward gradient flow. And all of these critical points are actually strict, at least, obviously if I have any solution and I move by a diffeomorphism, then I get another solution, but they're strict maxima modulo diffeomorphisms. So, well, one immediate consequence that's sort of different from Ricci flow is, for instance, that, well, on a compact manifold, then the volume is increasing along Laplacian flow. In particular, then I can't have, say, compact shrinking solitons in Laplacian flow, which is very different from Ricci flow or mean curvature flow, where, for instance, you can take a round sphere in either case, and that's going to shrink homothetically. So there are some obvious differences with Ricci flow and mean curvature flow. But once again, the general hope, and of course this is too naive, is that, well, suppose that I have a solution of Laplacian flow and that it exists for all time, then, well, maybe it will converge at infinite time to something that is a stationary solution, namely a torsion-free G2 structure. So that's the aim of any geometric flow, is to try to exist for all time, hopefully, and then at infinite time have convergence to some nice geometric structure. Okay, so in the parabolic PDE approach to torsion-free G2 structures would be try to prove long-time existence and convergence results for the Laplacian flow. So, well, let's just say a little bit about what sorts of things you might need in any geometric flow to have a hope of succeeding. So, the first thing that you need are at least short-time existence and uniqueness for solutions to your flow on compact manifolds. So in Ricci flow, that was, of course, due to Hamilton first, but then simplified by de Turck's trick. So we know the analog of those in Laplacian flow. Those were established by Bryant and one of Robert's former students, Xu. And the proofs there are, well, they're a little bit more complicated than in the Ricci flow world, in that the analog of the de Turck trick doesn't work so well, but still, if you're willing to use Hamilton's original version of the Nash-Moser machinery, then this is also kind of standard. So that's sort of, at least it's like a locally well-posed problem that you can start with any background closed G2 structure and you can flow it for a little while and there's a solution and it's unique. So other sorts of things that you would immediately hope would be some kind of, maybe if you've got a static solution, so you've got a torsion-free G2 structure, you give it a small perturbation, and then you ask, what does the flow do to it? So does the flow then exist for all time and then converge back to, well, either that original solution or possibly some nearby one? So this sort of long time existence via stability was proven in the case of Laplacian flow by Lotte and Way. So that's something that's desirable, but again, it doesn't give us anything new, that we have to know that there is a torsion-free thing there in the first place, and then we can give it a small kick. So something of a more technical nature are so-called Xi-type estimates, so higher-order derivative estimates. So in the Ricci flow case, this was due to Xi. In Laplacian flow, there's an analog of those, again, due to Lotte and Way. And those can be important because they can lead to finite time extension type results. So there'll be some kind of quantity, and that they will enable you to show that if this quantity remains bounded, then the flow can be continued past that. Or another way to say that would be that if the flow only exists on some finite time and is becoming singular at some final time, then this quantity is going to have to blow up. So in the Laplacian flow case, then the quantity that they write down involves taking norm square of Riemann together with covariant quantity constructed out of the covariant derivative of the torsion tensor. So again, this is another important ingredient that might help you say that the solution exists for not just a short time, but for a longer time. So another crucial kind of part of the package for any reasonable geometric flow is some sort of analog of Hamilton's compactness theorem. So Hamilton's compactness theorem gives us some conditions under which, given a sequence of Ricci flows, then we can extract a limit Ricci flow. And that sort of limit construction turns out to be crucial when trying to understand the behavior of Ricci flows close to singularities. So you zoom in again close to a singularity and try to construct a limiting Ricci flow, but which reflects something about what's going on at the singularity, but which in some sense will have some extra structure not present previously. So we have a Laplacian flow analog of these compactness results, also proven in the same paper, one of the same papers by Lotte and Way. But one crucial difference is these compactness results, so certainly the original Hamilton one and then the Lotte Way, they need to assume some sort of lower bound on injectivity radius. And so, but happily in the Ricci flow case, then, after Perelman proved the no local collapse result, then this injectivity radius lower bound is something that will be automatic for finite time singularities in Ricci flow. So the same is not true, is not known to be true in Laplacian flow at present. So we have only a partial analog of no local collapse for Laplacian flow due to Gaussian, but it needs to make an assumption, and the sort of assumption that you need is something like the torsion, or equivalently the scalar curvature, to remain bounded. So, clearly that sort of thing doesn't always hold in Ricci flow. So, if you're if you have a shrinking sphere, then its scalar curvature is not staying bounded. So it's not clear that this is, a reasonable assumption to always make. But it's the best that we know at the moment. Okay. So our ideal case in a flow would be establish long time existence and convergence as time goes to infinity to some sort of static solution. So the prototypical example here might be Hamilton's original three-dimensional spherical spaceform theorem, where you can start with any initial metric on a compact three manifold, assume that it has just Ricci positive, then you don't want to look at Ricci flow itself, because that's going to want to shrink this, but you have a normalized version of Ricci flow. So you have some corrections to stop the volume from decreasing. And then under this normalized flow, then he proves that you do have long time existence, and then you have convergence at time goes to infinity to Einstein metric with positive scalar curvature. And then because we're in 3 dimensions, then we just get a spherical spaceform. So that's a sort of ideal, but often that ideal is unattainable. So even in 3-dimensional Ricci flow, then long time existence or convergence to a static solution could both fail. And as we said, then the long time existence will fail when we encounter finite time singularities. So in Ricci flow, then there'll be some final time, capital T, and as T approaches this final time, capital T, then this norm of Riemann will blow up. So, but so finite time singularities are maybe hard to understand, but sometimes are your friend. So in 3D Ricci flow, it was understood that, of course, some sort of singularities were expected and needed, and in the 3D case, then Thurston's geometrization conjecture already gave you some sort of insights into what sorts of finite and then infinite time singularities you should expect might arise in 3D Ricci flow. So, for instance, then if we take the product of a two-sphere with R, then that's also that's a cylinder, and under Ricci flow, then the size of the S2 shrinks, so it's another kind of shrinking soliton, and then we don't expect that R. So the first thing that we have to do sometime in geometrization is to implement the connect sum decomposition of our three manifold. And so then neck pinch singularities modeled on these shrinking cylinders are the things that should be implementing our connect sum decomposition. But in general, we would need to develop some sort of theory of finite time singularity models. And then if as part of that singularity, finite time singularity model development, you can prove that only the expected finite time singularities arise. So if we only have things like neck pinch singularities, then we could hope to do this flow with surgeries. So so we have to have a modified version of the flow, which when it sees something like a neck pinch singularity developing, well, either you try to develop some weak notion of flow which allows you to really go up to the singular time, or in Kalman's original approach, then you would stop a little bit before and then do some surgery and restart again afterwards. So in that, then you would hope that you could repeat this. So you could do then Ricci flow with surgery. Ricci flow with surgery may then exist for infinite time.
I think we lost you again.
Yeah. Can you hear me again?
Yes.
So, apologies.
We don't see the screen.
Okay. Do you see the screen now?
No, not yet. Yes, now we do.
So for some questions, you will still have to analyze what happens in the behavior of the flow at infinity. So most of the Thurston geometries only appear at infinite time. And so, for instance, if you have to do something like this JSJ torus decomposition before you get the hyperbolic pieces, then you may have to look at the behavior. Does the flow see that at infinite time? But let's not look at infinite time singularities until finite time singularities are under more control. Okay, so that's the sort of general approach that one has taken in geometric flows. So let me just mention one kind of thing related to Laplacian flow, where some of these ideas are useful and have maybe given some of the strongest results that we have available that relate directly to Laplacian flow. And this concerns what is so-called hypersymplectic flow, which turns out to be sort of a reduction of Laplacian flow. And it also relates to a conjecture of Simon-Donaldson that on its face has nothing to do with G2 geometry. So if we have a four manifold, then we call a triple of symplectic forms on it hypersymplectic. If anytime you take a non-zero linear combination of this triple of forms, then that's also symplectic. So Donaldson conjectured that if you have a hypersymplectic structure on your compact four manifold, then in fact there should be an isotopy through cohomologous hypersymplectic structures that starts with your arbitrary hypersymplectic structure, but then at the end of the isotopy, then in fact the triple is not just hypersymplectic, but hyper-Kähler. So, of course, if that were true, then it would say that your original manifold was hyper-Kähler, and so that's obviously very restrictive for 4 dimensions. So most 4 manifolds would not admit a hypersymplectic structure. Okay, so why is there any sort of connection to Laplacian flow at all, or to G2 geometry at all? So the first observation is that if I start with a hypersymplectic triple, then on the 7 manifold that's T3 times my 4 manifold, then I can construct a 3-form phi. So if the TIs are the coordinates on your 3 directions of your torus, so then you take phi that's dt1 wedge dt2 wedge dt3, and then minus the sum of dti wedge omega I, and then sum over I. So when this is a hypersymplectic triple, then this 3-form is actually a closed G2 structure. So then you can run the Laplacian flow on it, and then Laplacian flow starting at that particular type of 3-form actually does descend and give you a flow of hypersymplectic structures on it. So a very nice result about hypersymplectic flow proven by Fine and Yao is the following. So again, suppose that you've got a solution to hypersymplectic flow with a compact 4-manifold, and it's defined on some finite time interval, 0 up to S, but you don't know that it extends to S. Then if the scalar curvature of this G2 structure, closed G2 structure, if it remains bounded on this whole interval 0 up to S, then in fact the hypersymplectic flow extends past that. So that final time is not the final time, you can keep going. And they also have some results about convergence as t goes to infinity, but with considerably stronger assumptions. So the nature of the proof of this is to use these results about possible finite time singularity models. So the Gao-Chen work applies. In this case, it shows that a singularity model that you would pick up would be actually a torsion-free G2 structure. The symmetry, the T3 symmetry, will actually force us to be, T3 times something, or split R3 times something, and then we'll have that this torsion-free G2 that we see must actually have Euclidean volume growth. So then that will, in this splitting force that we actually have on the 4-dimensional remaining factor, a hyper-Kähler ALE space, and then we know classification of them, and then using this classification, we see that some topology would be disappearing, and then there's a somewhat involved argument to show that that actually cannot happen. So you suppose that there were a singularity, you analyze what the singularity model would be, and then show that that singularity model couldn't have occurred, and therefore the solution persists. So, it is a very beautiful result that I would encourage you to take a look at yourself sometime. Okay, so let's say something about singularity models more generally. So in a geometric flow at a finite time singularity, if the flow enjoys some reasonable compactness properties, so like Hamilton's compactness theorem and this Laplacian flow analog, then close to the singular time, then you can rescale space and time in a way that respects the parabolic nature of the problem. And then because you're zooming in close to this singular time and the scaling that you're doing, this parabolic rescaling, then what you will end up with, thanks to your compactness theorem, is going to be another solution to the flow. It's going to still stop at, in general, it's going to still stop at some finite time. But now, previously, it just existed on some finite lifetime. But now this thing extends all the way back to time minus infinity. So that's what's called an ancient solution to the flow. And so that's the extra structure that you pick up when you pass from just a solution to the flow to now you're looking at the finite time singularity of a flow. What you get for subsequential limits are ancient solutions to the flow. So in Ricci flow, then because of no local collapse, then we don't just see any old ancient solution from finite time singularity models. You see ones that have some kind of non-collapsing behavior. So they're so-called kappa non-collapsed on all scales. So in 3D Ricci flow, then Perelman conjectured a complete classification of these kappa non-collapsed ancient solutions. But that wasn't resolved in his original papers and has only very recently been resolved by a combination of authors of Anganon, Brendel, Toti Daskalopoulos, and Natasha Sesson. But there are 4 ancient solutions, but I want to concentrate on 3 of them, which are solitons. So a soliton being a self-similar solution to the flow. So I'll be more specific about that in the Laplacian flow context shortly. So in 3D Ricci flow, there are shrinking and steady solitons, and these provide 3 of the 4 ancient solutions that are kappa non-collapsed. So we've come across 2 of these already. So the first is just a shrinking 3-sphere. The second is a shrinking round cylinder, that's 2 times r. And the third kind is a steady soliton constructed by Robert Bryant that is rotationally invariant. And so it can be constructed by solving some ODEs. But anytime we have either a shrinking soliton or a steady soliton, those will always give us examples of ancient solutions. And so before we can hope to understand general ancient solutions, we should try to understand its shrinking and steady solitons. And in this kappa non-collapse world, then 3 out of the 4 ancient solutions are solitons, and the 4th one is somehow constructed also using the Bryant steady solitons. But it is not itself a steady soliton. Okay, so let's now then head towards where the rest of the talk will be, which will be what can we say about solitons within the context of Laplacian flow. So we want to think of solitons as providing us at least key models for singularity formation, because they always give us ancient solutions. They may help us understand more general ancient solutions, but we'll also see that they can sometimes give models for singularity resolution. So specifically, what's a Laplacian soliton? So we've got a G2 structure phi, a vector field x, and a constant, call it the dilation constant lambda, so that it's a closed G2 structure. And now if I take the Laplacian of phi, then that should be lambda times phi plus Now the Lie derivative of phi by x. So I'll call that the Laplacian soliton equations. And then these are in one-to-one correspondence with self-similar solutions to Laplacian flow. So the line below gives you the dictionary. It tells you that given a solution to this, then up to movement by a diffeo f and an overall scale factor k of t, then we get a solution to Laplacian flow. And then maybe the most important thing to notice at the moment is this kappa of t is a affine function of t, and then the key thing is the sign of lambda. So if lambda is negative, that's what we'll call a shrinker. So in that case, then we want this, so this kappa can exist all the way back. So the solution can exist backwards to the time when this becomes 0 or negative. So this can exist back to minus infinity. If lambda is 0, then we can have a solution that exists for all time. And then in the lambda positive case, these are called expanders. And so they yield so-called immortal solutions to the flow. So they start at some time, but then they exist for all times after that. So we have ancient solutions as relevant for, or ancient or eternal solutions are relevant for forming finite time singularities, and expanders, immortal solutions are relevant for trying to understand if we have a singularity, then maybe the flow can pass through the singularity and smooth out of it. So we'll see that later in the talk. So if we just look at the second equation and apply Cartan's formula, then of course we see that if we have a non-steady Laplacian soliton, then that means that the 3-form must be exact. From what I said before, because of the gradient flow, upward gradient flow for Hitchin volume functional, then it's not difficult to see that on a compact manifold that so we can't have shrinkers, and then if we can't have non-trivial steady solitons, they have to actually be stationary, and we can't at the moment exclude expanders, but currently no compact expanders in Laplacian flow are known, and it's an open problem whether they could exist. In fact, I think the weaker problem of even just finding a compact manifold for which there is an exact G2 structure is also open. So without satisfying the equation, just this topological condition of being exact. So the first question again is sort of a local question. This again looks like a highly overdetermined system. Maybe it's so overdetermined that you don't get solutions to it, but again, much more recently, Robert has studied this problem, again using methods of overdetermined PDEs, and at least for generic vector fields, so things that are not gradient, then the local generality of solutions is understood. The case where X is gradient is still mysterious. So, but again, the question then is not about the local nature of solutions, but global solutions. So either compact expanders, or in these other cases, then non-compact complete solutions. So we don't have any general analytic machinery to construct global solutions to the Laplacian soliton equations. We certainly have the same problem in Ricci flow, except more recently in the Kähler setting. So to make some initial progress, then we need to study solitons that have some additional geometric structure. So what I want to talk about is looking for, so this additional geometric structure is being somewhat symmetric, so having cohomogeneity 1 action of a Lie group. So a Lie group acts with generic orbit of codimension 1, and so then we should expect that the PDE system reduces to an ODE system, and of course that will be considerably simpler, although definitely non-trivial in the end, still to study. And we'd like to concentrate on things that we at least think might be potentially viable models for finite time singularities, formation, and their resolution. So more specifically then, well, if we go back to we in the torsion-free world, then of course, going back to the original Bryant-Salomon paper, which first constructed non-compact complete torsion-free G2 structures, then on lambda 2 minus of either CP2 or S4, they both admit cohomogeneity 1 G2 structures with either symmetry group SP2 for the 4 sphere or SU3 for CP2. And these torsion-free G2 structures are exact. They're asymptotically conical with some rate -4, and they become asymptotic to cones over either CP3 for S4 or the flag SU3 mod T2 for CP2. And then each of those 6 manifolds admits a unique homogeneous SU3 structure that makes the cone over that into a torsion-free G2 cone. And then we have these asymptotically conical torsion-free G2 structures on lambda 2 minus of these two spaces, and up to scale, those things are unique. So here we instead want to study solitons on these two spaces with the same symmetries as the torsion-free ones, but now we're looking for either shrinkers or steady solitons or expanders. So, so the first result is something about shrinkers. So it says that on both of these spaces, then in fact there is indeed an explicit complete cohomogeneity 1 shrinker. It has rate different from the torsion-free one. It decays more slowly. And again, it's asymptotically conical, but now the asymptotic cone that we get is not a torsion-free cone, as in the previous case. It's some closed invariant G2 cone that is not torsion-free. Given that, you could look at all the possible cones that might arise this way and try to study kind of ends of shrinkers. So the second theorem says, so we take either of the symmetry groups that are relevant, SU3 or SP2 in the CP2 and S4 case. So then we look at a closed G invariant G2 cone C. Then the statement is that there's a unique G invariant shrinker N, so something that satisfies the shrinker equations, but that does not necessarily extend all the way to give us something complete. It just gives us something on kind of collar neighborhood of infinity. So it's easy to see that the space of G invariant cones is either one-dimensional in the SP2 case or two-dimensional in the SU3 case. So this theorem gives you continuous families of shrinker N's. But our conjecture is that this explicit AC shrinker that we have, in the case of S4, is the unique, complete asymptotically conical shrinker, SP2 invariant shrinker. And you could also then just ask, well, let's look at AC shrinkers asymptotic to one of these cones. And so don't assume symmetry. So assume the symmetry of the cone, but not of the shrinker. Then the answer should still be the same. It's still, this should be the only one. And then, well, something not as strong would be should be true in the SU3 case, that even though we have two-dimensional families of shrinker n's, then only a finite number of those should actually be completable into a complete SU3 invariant shrinker. So the upshot of this conjecture is that most of the shrinker n's that we know exist should not extend to complete shrinkers. So in some sense, that's good news, or that should be good news. We hope that, since shrinkers model singularity formation, we hope that shrinkers are either relatively rare or rather rigid geometric objects. It's not always clear how to quantify that. So, for instance, if we have an asymptotically conical Ricci flat space and we look at its asymptotic cone, then its asymptotic cone is still Ricci flat. And then that could put substantial restrictions on the cross-section of that cone. But typically, the asymptotic cone of an AC shrinker does not need to be satisfying any equation, any obvious equation. In particular, it's not a shrinker itself, typically. So a priori, this seems like it makes AC shrinkers hard to classify because you can't kind of proceed by analyzing the cones directly. On the other hand, then there is a way in which shrinkers are more rigid than, say, asymptotically conical Ricci flat spaces in the following sense. So if you have at least an asymptotically conical Laplacian shrinker where the vector field is gradient, then in fact, any end of it is completely determined by its asymptotic cone. So for a given cone, there might not be a shrinker, but if there is a shrinker, then it's unique. Then secretly, the cross-section has some extra structure, so the cross-section of any cone of such a shrinker is actually real analytic. And then there's a certain amount of structure that is inherited. So if you have a symmetry, including discrete ones of the cone, then they in fact pass to the end of the shrinker. So for instance, this allows you to reduce the classification of shrinkers that are asymptotic to cones with symmetry to shrinkers with that symmetry. So in particular, if we're studying things that are asymptotic to SP2 or SU3 invariant cones, then that reduces this shrinker classification problem from an ODE problem, from a PDE problem to an ODE problem. And so such theorems similar theorems are known in the context of mean curvature flow and Ricci flow due to Liu Wang and Brett Kochvar and Liu Wang respectively. And sort of in essence, then they're a manifestation of some very strong backward unique continuation results that parabolic PDEs enjoy. So it's a sort of surprising amount of rigidity that they have. So a natural question is, well, we wanted to find shrinkers that were possible models for finite time singularities. So do these actually appear? So at the moment we don't know. So things like analogous questions in Kähler-Ricci flow are understood. So for instance, there are some shrinkers with symmetry that were found by Feldman, Illman, and Knopf, and they have a symmetry, a U2 symmetry. If you study U2 invariant metrics on certain compact Kähler surfaces, then you can indeed show that those arise as finite time singularity models. So we could try to do something similar in Laplacian flow. The main difficulty is that it's much more difficult to get closed G2 structures on compact manifolds with a lot of symmetry. So that's sort of the obstruction here. But there's a variant on this thing that, at least in the non-compact world, seems more approachable. So you could ask, well, if I stick to the non-compact world and I continue with the same symmetries, then can I at least find solutions to Laplacian flow on the same space that are not themselves solitons, shrinkers, but which develop singularities modeled on those? So in that case, then you can hope to use barrier methods to try to control things. But if the answer to this question is yes, then this raises a kind of pressing question. So is there a way to continue Laplacian flow past this first singular time? And is there a way to make it continue past this singular time on a smooth space, or are you forced to perhaps consider flowing G2 structures that have some sort of conical singularity? And then, well, the answer to question 2 currently appears to be sensitive to whether we're talking about the shrinker on lambda 2 minus of S4 or lambda 2 minus of CP2. And to see the reason why there's a difference, you have to think about expanders. So let me just so going back to Feldman, Illman, and Knopf, it's probably beyond, besides this in mean curvature flow, then in other geometric flows, then it's a reasonably common phenomenon is there can be a common asymptotic cone which can appear as the asymptotic cone of both a shrinker and an expander. And so then out of that pair of a shrinker and expander, you can define a sort of weak solution to the flow that looks like it's the shrinker for all negative times, it's just the cone at time 0, and it's the expander for all positive times. And this gives you some sort of weak solution to the flow that at time t equals 0 is exactly the cone. So Feldman, Illman, and Knopf call this flowing through the singularity. And in Kähler-Ricci flow, then there is a shrinker due to these authors, an expander due to Huidong-Zhao, and it models blowing down, say, a -1 curve in a Kähler surface. So, this motivates us to consider expanders in Laplacian flow. And so let's start with the sp2 invariant case, so on lambda 2 minus of S4. So it turns out that there's a one parameter family of these complete sp2 invariant expanders. And then we can completely characterize what the asymptotic cones are. And there's a one-dimensional space of these cones. The torsion-free one sits in there. It disconnects that space. And then it turns out that all cones on one side of the torsion-free one arise this way. However, the cone of the shrinker that we found is not on that side. So this leads to a sort of a no flow through theorem, at least in this sp2 invariant case, that says there is no complete expander whose asymptotic cone is the cone of the shrinker. So we don't know whether or not this holds without the symmetry assumption, but we think that maybe that's the case. And if that's the case, then this suggests that to continue the flow, you really do have to consider continuing it as something singular. Okay, so then the answer turns out to be different. We conjecture the answer is different for CP2, but because of time, I think I will just stop there.
Thank you.